Hello everyone, welcome back to the channel. Before watching the video, please do subscribe the channel and watch all the previous videos so that it will be easy to follow upcoming videos. Okay, let's go today what we are going to discuss. In previous video, we have discussed a linker file, how linker file we have to write, how it works, everything we have explained in the previous video. Today we are going to start with the startup file. How linker file is used in startup file, how startup file is used in embedded systems. Today we will go through all these things. So first we will create a file with the .s extension and we will start with the syntax unified, meaning it will be used whenever we are using ARM and thumb instruction set. And we are using CPU Cortex-M4 controller for STM32 and we are using thumb instruction set. So this is mandatory for STM32 startup file. Then we will use .global underscore e stack, which is declared in linker file. So we are going to use this in startup file. So we are using this label in startup file and dot global reset handler. This one also we have declared it in linker file. This is the entry point of the program and we are declaring it in startup file and we have considered this as a global. Dot extend main. So we are going to create a function called main in main.c file and we are going to create one more function extend system init. So this function will be called a before main. So here we will do some initial configurations before main. So we are declaring the function here and we are using it in startup file. So that is why we have used extend in startup file. So I will create a function, dummy function now, void main void system init. So I'm using extend here to get the function in startup file. This is just I will create dummy function. So the function definition is defined in another file. That is the meaning of this extend, and I'm going to use it in this file. And I will create a section dot isr vector. So the section isr vector I'm going to use, and the code what I'm going to write further will store it into that particular section. So here I have created a isr vector section and it will be stored in flash. So whatever I'm creating in upcoming lines, it will be stored in this particular section. I will create a dot word e stack. So meaning the first address will have the main stack pointer, which is the last address of the RAM, and the second address will have the reset handler. From this, our code will start execute. So the first instruction is main stack pointer, second is reset handler. Is the first function it is going to execute after initializing the stack pointer. Next, I'm creating dot section dot text, meaning the further I will create a reset handler functions. All these functions has to store it in dot txt section. So I will create a function reset underscore handler and I will jump the system init function from here. So after main stack pointer initialization, reset handler function will execute. Here branch to link, which means BL branch to link means jumping to system init function. So here we will do all the initializations. Then we are once the system init is completed, then we are going to jump to main function. There our main application code will be integrated. Now I will add one more function after executing reset handler, loop forever. Here we will create a one more function called loop forever. B means branch and loop forever. I missed to add underscore. Uh, Sorry, we can remove the space, and I will paste loop forever, which meaning it will keep on looping like while one loop. Okay, this is the minimal startup file for STM32 F44 6RE. Once this is done, we have to do uh, zero BSS sections need to be cleared and the data sections needs to be initialized after the startup. Here I will add one more thing, comma a, which means allocate, comma percentage program bits, meaning allocate the code and datas into this ISR vector section, meaning the first address of the flash. And the function calls reset handler loop forever will be stored in .txt section. Now we will start implementing the system init and main functions what it needs to be there. First we will include standard init header file. So std_init.header file. Then we will fetch the labels from the linker file. So we have a linker symbols we already created in a linker.ld file. So I'm going to use it in this file, extend uint 32, which is 32-bit address instructions, underscore si data. This is the start address of the initialized data, which is stored it in flash, and we have to copy that data into RAM location. So I will fetch the linker labels first. All the linker labels I need to access it in a main.c file. Start address of data section. This is for RAM address. Extend uint32 underscore t. End address of the data section in RAM. Extend here you can see this data section start address end address will be stored it in RAM. And now I'll add uint32 underscore t underscore start BSS, meaning start address of the BSS section in RAM. Extend uint32 underscore t underscore e BSS, end address of the BSS section in RAM. And I will create two functions. One function is for initialization of data section. I will declare here static void BSS init. Here we will clear the BSS memory regions. It should be initialized with 0. Now here you can see in startup file we have system init before main function. So first we have to initialize the initialized variables in data section. So I will create a initialization of dot data section. Since the initialized variables will store it in RAM, but the values will be stored it in flash. So we have to copy that flash uh, initialized value to RAM. So I will call this function first, data init. Then I will call BSS init. So here all the variables will get initialized during startup. I will call BSS init function. Yeah, now we have to implement these two functions, how the flash is copying, how the initialized data is copying, how the BSS memories are getting cleared with a 0. I will create a function definition here. So first we will declare a local variables uint32 of source address of the flash memory. So pointer variable I'm creating, address of underscore SI data, source address of the data section which is in flash. I'm storing it in SRC. Destination, I have to copy this to RAM. I'm creating one more pointer variable and I am storing the destination address, the start address of the data section in RAM. So we have to copy from flash to RAM. So I will use a while loop, destination less than address of end address of the data section. So it will copy uh, from flash start address to end address and it will store it in RAM. So here it will copy from flash start address to RAM start address and we have to iterate the address so that it will keep on copy 32-bit every time until it reaches end address of the data section. So we have to increment this address. I'll add it dst increment and source address also I need to increment. So the initialized data will be copied from flash to RAM by using this particular function. So mostly these functions will be implemented in assembly code. So you can able to implement either in assembly code or a .c code. Now we will add the command for this function. Copy initialized variables from flash to RAM. This is the purpose of this particular function. Now we will create another function which is clear uninitialized data in BSS section. By default it will have some garbage values, so we have to clear with 0. So static void BSS init. This function also should be implemented similar to data init. The only difference is instead of copying from flash we will assign it with 0. So the destination address we will consider as start address of the BSS section. The destination will store the address of the BSS start address. Here we have initialized in uh, this linker file. Here you can see this is the label we are using to get the start address of the BSS section. Now we will use same while loop to iterate the address of the BSS section. DST less than end address of the BSS section. So the loop will continue until it reaches the end address of the BSS section, and we will assign each address with 0, and we will increment the destination address for each iteration so that it will clear all the BSS section with 0. So now we can see in SystemInit data initialization and BSS section initialization, everything is implemented. So this function will call before main function. So now we will implement a main function. So once we entered the main function, our application code has to run. If main function has no while loop, it will come to loop forever, and it will keep on staying in that loop forever. So instead of going to startup file, here we will create a while loop, and we will make the control inside the while loop. All our application codes we will implement it inside the while loop. Here we have written this hatch as a small letter, so we have to make it higher since it's a case sensitive. Okay, now we have implemented almost main function, startup file and linker file. All these files have been implemented. Now we have to understand how all these files are compiling all together. So we have to understand the compilation stages and all. We will see it in the next video. And now we have to understand how the files are getting compiled and how it is linked. First we have to compile main.c startup file, and these object files needs to be linked using linker.c file, linker.ld file. So first I will compile main.c gcc. First I will check the gcc version is installed or not. Yes, in my system it is already installed. In case if your system is not installed with gcc, it won't compile. So if you have not installed, please go through my previous video, ARM based GCC cross compiler installation. You can able to see this. Once your version is there, now you can compile your files. Now I will use my compiler -c main.c -o main.o. It will create a main.o object file from the .c file. You can see now my main.o file is generated. Now the same way I have to compile my startup file, which is in startup folder. So I have added the folder path, and I will create a object file for startup file. You can see object files also created. Now I have to link these object files based on my memory mapping. So I will use this first compiler, and I will add the object files. -t is to link the linker file, and no standard lib is for not to use the Windows library. So that is why we have to use this. And this WL and map to create a map file for my ELF file. So it will create a ELF file and map file. Okay, there is some error. Let me analyze this. Okay, so the main.c file we have to compile with the thumb instruction. Since the startup file we have already defined what to do. So that dot thumb we have added in the startup file. So it is compiled properly. But for main.c it is compiled like PC. So we have to add this -m CPU Cortex-M4 -m thumb. So it will compile based on the ARM controller. Now we can use this command. Now we will enter this. We can able to see ELF file, map file, everything is generated based on the linker file. Now you can see the flash address and all it is showing as per the linker file. RAM address also is there, and based on the linker file only, this ELF file and map file is created. So this ELF file you can able to flash directly into your controller. Now all your sections will be placed into respective sections. So you can go through this file, you'll understand more about how, however you want your sections to be placed, it will be placed in the .map file. You can verify it here. Some of the extra sections are there. This is based on the ARM controller things. So you can verify only your sections what you have defined in the linker file. Yeah, we will see more about compilation stages in the upcoming videos. How uh, how each stages are working, all these things we will see. Next video we will see how makefile will be used. Instead of giving multiple commands, we can use a single file and we will run all the commands in a single command. Yeah, thanks for watching the video. Do subscribe for the channel.